Oh, lovely.
Yeah, thanks for that, Jesse. Welcome, everyone. Welcome to NECA's presentation on the new Australian Standard 5033, the installation safety requirements for photovoltaic arrays. I'd like to welcome our team from across the country. It's great to have such a broad representation from all of our technical team. This, just so people know, this is being recorded. The recording will be available on our TKB, as well as the slides and any Q&A. This standard has been a long time coming. We're going to focus our webinar today on the major changes. So we're not going into a deep dive, but we will focus on the major changes that we see for our members in the industry. It's a new standard, so it's not an amendment. So if you do have an old copy of the 2014 version, feel free to throw that in the bin and find yourself this new copy, this new 2020 version. As I said earlier, all Q&A will be available on TKB. If you do wish to ask a question to be answered at a later date, on the bottom of your screen, there's a tab that says Q&A. Press on that and ask your question, and we will record it and answer it at a later date. Just over to the team, we're lucky enough to have our representation today from across this broad land. As you can see there on the screen, we have Michael and Lewis from NECA Victoria. We have a representation from New South Wales, ACT, Queensland and Tasmania from Hannah, Michael Horsham and Grant Morehouse. We have Malcolm over in WA and myself representing the NECA National Office. Just a reminder again, if you ask any questions, then please do put them in the chat. We will get to them when we can. Otherwise, sit back and enjoy the knowledge of this great, wonderful team we have. Over to you, Grant.
Thanks, Paul. So 5033 was published on the 19th of November 2021. For New South Wales, it was implemented from the date of publication. All other states, it is not in force until 19 May 2022. So at the moment, for every state other than New South Wales, 5033 2014 is still current. So after the 19th of May 2022, you will have to use the new version. You can, if you want, use the new version now, but you must do it in its entirety. You can't mix and match. Throughout this presentation, all clauses referenced relate to 5033 2021 unless indicated otherwise. This standard does not apply to installations less than 100 watt and less than 35 volt DC open circuit voltage at STC, transportable structures, vehicles that are in accordance with AS NZS 3001, boats in accordance with AS NZS 3004, and PV arrays on large-scale ground-mounted PV power plants with restricted access to personnel and connected to dedicated high-voltage systems. However, with absence of an Australian standard for these systems, this document should be used as guidance subjected to engineering principles. Terms and definitions. So there are some changes to the terms and definitions. Clause 1.3. If a definition does not exist or listed in this standard, then the definition in AS NZS 3000 shall apply. You will see the adjacent definition in the previous version has been removed, 3 metres. Now you shall use AS NZS 3000 definition as below. So clause 1.4.6, next to or adjoining without obstruction and within arm's reach. Clause 1.4. Notation. So throughout this standard, this will take a fair bit of your time to grasp. So you need to keep an eye out for those notations. Application circuit clause 2.1.1. Basically, it's just defining what this standard and what the array circuit application is. So it gives you an example, grid interacted or off-grid systems or microinverters. Restricted access clause 1.3.37. So there is two new parts of this, and I'll go into that in a sec. By barrier, so by perimeter fence with access only via a padlock or secured gate or door. By location, so example, roof where there is no fixed ladder or other ready means of access. The new one, item 3 and 4, by enclosure, example, cables in a wire enclosure that is not accessible without use of a tool, or by installation height, so greater than 2.5 metres above the ground, floor or platform. Ground mount arrays, clause 43232, where PV modules are within 2.5 metres from the ground, floor or platform, and are not installed on a roof, restricted access shall be provided to PV modules and wiring systems up to the disconnection point. Any ground mount installations not greater than 2.5 from the ground, floor or platform, shall have restricted access. A suitable perimeter fence shall be installed with access via a padlocked or equivalent secured gate or door. Maximum voltage limits, clause 3.1. Calculated maximum voltage for PV DC circuits for domestic electrical installations shall not be greater than 1000 volts DC. Calculated maximum voltage for PV DC circuits for other electrical installations shall not be greater than 1500 volts DC. Clause 4.5.2.2, grid connect inverters. The installation of grid connected inverters shall be in accordance with AS/NZS 4777.1. Note, AS/NZS 4777.1 2016, clause 2.3, this is the current version, still states systems with a maximum voltage of 600 volts for inverters connected to the grid. This only applies to grid connected systems. Standalone systems, you can go to 1000 volts DC for domestic. And until 4777.1 2016 is rewritten or an amendment is in place, then this standard shall prevail. Over to you, Lewis.
Yeah, thanks, Grant. Now we're just going to delve into the maximum voltage calculations. There's actually not too much of a change in determining the maximum voltage calculations for the minimum or the lowest temperature. And we still have table 4.4 to simplify calculations by using a correction factor if PV module data is not available. Strings constructed using DC conditioning units, clause 2.1.5. The clause explains different arrangements regarding DC to DC conditioning units. Full and partial arrangements have been identified. You can see this in figure 2.7 and 2.8 of the standard. The voltage determination for each string as per clause 4.2.1.3 shall be applied when using DC conditioning units. Note, voltages in a string determined by each DCU maximum voltage, or if full deployment, then the rating of the inverter's maximum rating can be used if it meets the requirement of IEC 62548. The new formulas. Systems with no DCUs, just your normal string inverters. So the string maximum voltage equals the V mod max times the amount of modules. Systems containing partial DCUs. So you've got the VDCU string max equals the VDCU max times the number of DCUs in series plus the V mod max times the amount of modules. An explanation is that you could have 3 DCUs on a given string. You have to take in the voltage of those 3 DCUs and add the voltage of the remaining modules without DCUs. Systems containing DCUs on all modules, it's the DCU max times the number of DCUs in series. Note, inverters meeting IEC 62548 can use the rating of the inverter max voltage on its nameplate. You will also see in the notations that we have a capital M and small m. And they both have different meanings. Here you will see an electrical data example of a DCU. You will see that the voltage is at 90 volts. And let's have another look down there at the recommended fuse rating of 15 amps. Protection against overcurrent. PV modules may be connected in parallel and directly connected to external sources, example batteries. These additional sources increase the amount of current under fault conditions to the PV array, cables and components. Contact the manufacturer's potential backfeed currents of external devices. Containing no DCUs, the string max equals 1.25 times K times ISC of the module. You will see the addition of the K. We'll talk about that a bit further. Strings containing partial DCUs, it's the greater of A or B. So the string max equals, could be IDCU string max. Strings with DCUs on all modules, the string max equals the IDCU string max. Calculating potential string fault when you need it. SA in that formula is the amount of parallel strings in that circuit. That formula hasn't really changed at all. So it's still take one off times the I string max. What's changed is the I string max. When strings are connected in parallel, overcurrent protection shall be provided when the potential fault current plus the backfeed current exceeds the maximum overcurrent protection rating. Overcurrent protection rating calculations, clause 3.3.5 and table 3.1. This gives you a guide of what size string fuse ratings will be required in those parallel strings. The new table incorporates DCUs. Note, added the OCPR of the DCU to be considered. So what is the K factor? That formula we had before, 1.25 times K times ISC of the module. K is for bifacial type modules. If not using, then the value is 1. If using bifacial type modules and they are installed where very limited light incident is on the back surface, example, roof with modules close and parallel to the roof, the K value shall be 1. The value of K is available from the module manufacturer datasheet or Appendix J, which is a normative reference table. Appendix, sorry. Over to you, Grant.
Thanks, Lewis. So there's a new clause here, clause 3.4. It's been added to be aware of DC connections for correct tightening to avoid points of failure. All connections are locked in place. All crimp connections are performed according to manufacturer's instructions. Appropriate materials are to be used for contact and the connections. So example, not using dissimilar metals. Plugs, sockets and connectors. So clauses 438 and 439. There's additional information there. Conforming all connectors, plug sockets need to conform to AS/NZS 62852. No change in some parts. So they shall be mated with those from the same manufacturer and designed to be mated together. So you can't mix and match sockets, plugs and connectors. Be terminated using a tool designed for the purpose as specified by the manufacturer. Module junction boxes, clause 43226, where modules are installed in such a way that a junction box is to the side or at the bottom of the panel. Care should be taken, at the inverter, care should be taken at the panel, care should be taken to ensure that it is in accordance with manufacturer's requirements. And note, some manufacturers require module junction boxes to be at the top when mounted, having cables pointing downwards. Segregation and termination, clause 4.4.3.2 shall be achieved, segregation shall be achieved by separation of 50 mil or greater between DC circuits and non-DC cables. Where DC circuits are installed within 50 mil of non-DC cables, at least one shall be installed in medium-duty insulating wiring enclosure. Clause 4.4.3.3, termination of cables. Where DC circuit voltage exceeds 35 volts, double insulation or a segregation insulation barrier equivalent of double insulation shall be maintained up to the termination point. Lewis, over to you.
Yeah, thanks, Grant. Probably what everyone's been wanting to know the answer to. Disconnection device or disconnection point. You can choose. Clause 4.3.5.2.1 and figure 4.2. Systems where a maximum PV DC voltage exceeds 120 volts. You can use a low break disconnection device on the roof if you wish, similar to what you're doing to the 2014 standard with some extra requirements. If able to use a disconnection point, you have additional installation requirements. Are there more than 2 parallel strings? The standard gives you a decision tree. So just follow this decision tree. If there's not more than 2 parallel strings, you can basically go to no additional low break disconnection required on the roof. If there is more than 2 and they got string fusing, and the string fusing is back down at the low break disconnecting device or disconnector, which could be at the inverter, then you may be able to use it. But use this decision tree. It basically gives you all the answers to what you need to know. If you are using a disconnection point, clause 4.3.5, the disconnection points, which are MC4 plugs and sockets, shall be adjacent to the PV modules of the PV array. They shall be readily available, be protected against weather and water, and no more than 150 millimeters from the edge of the PV modules that they are installed under. Adequately supported so that there is no undue stress on the connection, but still able to be disconnected. Have both positive and negative disconnections located together, labeled, see clause 5.5.2.2, and documented on a plan, see clause 5.6. They shall be installed under the panel, not more than 150 mil from the edge, so as to be readily available. Here we've just got a picture showing where you would put it. Now that on that module, that could be at the bottom of the module, but basically 150 mil from either edge. You will see that there's a label that you have to put on the module itself. And you also have to put some additional labels on the cabling. Here's a closer view of those labels. A sign on the cable, both positive and negative, within 100 mil of the disconnection point. That gets put on the cable. This other sign, the PV string disconnection point, with those words, is attached to the PV module within 300 mil of that disconnection point. So have you decided a low break disconnection device or a disconnection point at the array? A disconnection device, not too many changes. Existing conduit arrangements within ceilings, walls, and under floors. The mechanical protection still remain. If you decide to go with a disconnection point using MC4 plugs and sockets at the array, same mechanical protection. But we do have specific conduit zone requirements will be required and discussed further. Here we have an interesting picture. You will see that the orange line is basically your conduit run. So this is from the external wall. So once you get to 1 meter from the inside of an external wall, you must start to go up to a 600 mil clearance from the bottom of the ceiling. In that section between 1 meter and 1.5 meters, that section of conduit has to be supported on the roof structure. Once you get beyond the 1500 mil, it's got to be 600 mil above the bottom of the ceiling. You can also still go down a wall cavity if conditions prevail. And the conduit still has to be labelled every 2 meters. But be in mind of also the 50 mil clearance in AS NZS 3000 that applies still in this arrangement. Wiring systems when using disconnection point, MC4 plugs and sockets, where you have conduit entering a ceiling space that is greater than 0.6 meters or 600 mil, you are limited by 200 mil on each side of a vertical plane of the isolator as shown below. If the ceiling space is not greater than 600 mil in height, it shall not be in that ceiling space unless the wiring system is located within that 1 meter from the internal surface of an external wall. This arrangement would be maybe when installing disconnection devices with inverters in garages where above the ceiling is greater than 600 mil. So you've basically got a 200 mil space on each side of the isolator where you can go up into the roof space. This is one of the first methods that's in the standards. You can actually, the cables running from the PV array down to the isolator or even the inverter, the conduit ends can be actually open ends on both ends. Well, you have to have open ends on both ends. The problem within the standard, you are allowed to have 300 mil of exposed cable, as you can see on the bottom, where it goes into that multi-hole gland on the isolator. The problem I see is that people can pull on that cable and put strain on the cable up at the array. I've made a note there of clause 3.3.2.8. Wiring system shall be selected and installed so as to minimize damage to the cable insulation, sheathing and connections during installation, operation and maintenance. I do not want to see people pulling on that cable at the bottom and basically cutting the cable through via the stainless steel ties, causing a bigger problem. Possible solution. At the bottom of that conduit, we can still have it open-ended at both ends, but we can put a T at the bottom, having a gland, and then we also have a gland going into the isolator or inverter. This way, if anyone pulls on those cables, the gland is going to retain movement and hopefully doesn't create any movement up top on the roof. I feel that this is a better solution. Now, where sections of conduit are installed in an outdoor environment and have conduit which terminates into an enclosure, a suitable drain device shall be installed at the lowest point of the conduit system. This device shall be rated at least IP56. See clause 4.4.7.2.3. You must use a multi-hole gland at the array end in this situation. This applies only when you've got the conduit going directly into an enclosure. Over to you, Malcolm. Malcolm there?
Yeah, enclosure entries. Thanks, Lewis. Clause 4.4.7.2.2, 1 and 2. If using side entries for a gland, the gland must be higher than the cabling. This is to enable a drip loop. Only manufacturer's entry points to be used. Do not drill your own holes against the manufacturer's instruction. Load break connection devices, fire prevention, clause 4.3.5.3.1. You must meet one of the following. It shall be mounted on a non-combustible material which extends 200 mil beyond the side of the load break disconnector, or be contained in a metal enclosure of at least 0.2 millimeters thickness, or be mounted on non-combustible shrouds that are made of 0.2 millimeter thickness and meet the requirements of clause 4.4.7.3b. Protection against weather and water for enclosures. Clause 4.4.7.3, enclosures containing switch disconnectors shall be mounted realistically between the 30° from the soffit, or will be provided with a shroud. Appendix K is normative, it has examples of these. Example, okay, dimensions of a shroud. To enable the 30 degrees, the shroud would have to extend beyond the isolator, and in the case of most DC isolators would need to be a width of about 490 millimeters. Note that after working out the standard DC isolator measurement, you would require this amount. Figure K, Appendix K, figure K2. This provides this. Protection of the shroud. Appendix K is normative. Shrouds reduce the possibility of water pooling on the joints and seals of the DC isolators. They should, if the shroud is made of 0.2 millimeter thick sheet, then it meets the protection requirements of the combustible surfaces in clause 4.3.5.3.1. Again, figure K, Appendix K, figure K3. Okay, pressure equalization valve. Clause 4.4.6.2, enclosures containing disconnectors shall be installed, device installed in an outdoor environment shall have pressure equalization valves fitted in the enclosure. There is an exception to this, unless the pressure equalization valve is integrated into other parts, such as cable glands or drainage devices, provided they are installed within 300 millimeter of the enclosure. Over to you, Michael.
Thank you, Malcolm. Earthing, clause 4.6.2. Where the calculated PV DC circuit maximum voltage is greater than 35 volts, the following shall be earthed. All conductive PV module frames, the array mounting frames that are directly in contact with the PV DC cables, and conductive cable support systems or conductive wiring enclosures that are directly in contact with the PV DC cables. Examples would be cable trays. Note, if the DC cables are enclosed in insulating conduit, then it is not deemed to be direct contact. The image on the bottom of the screen shows the unstripped earthing conductor with the clamp down. That's an excellent example of how not to perform that activity. This is figure 413. It's a detailed decision tree, helping you make the correct decision on the size of your earthing conductor. We won't go through it here at this point in time, but familiarize yourself with this particular decision tree, as it's imperative to you selecting the right size conductors. You still require a minimum 4 mil earth to the frame for durability reasons. The inverter separated type is generally a minimum size of 4 mil. Inverter non-separated is sized according to the DC arrangement, example with or without DC overcurrent protection. And if no DC overcurrent protection may be required, to be sized to the active conductor of the inverter AC cables. That's according to table 4.6. Labeling. Clause 5.4, fire and emergency information. They shall have a circular green reflective sign of 100 mil in diameter with the letters PV located at the main metering panel and main switchboard. DP is where a disconnection point is used as the isolation method at the array. SW, where a load break disconnection device is used as the isolation method. And AC for inverters, where the calculated PV DC voltage is less than 120 volts DC at the inverter input, generally a microinverter type. Over to you, Lewis. Oh, no, sorry. The access point in the ceiling. If the PV DC wiring systems between the disconnection point and the load break disconnection devices are installed in an accessible ceiling space or accessible floor space, a warning label shall be installed adjacent to the access point. Example of that label there. Thank you. Over to you, Lewis.
Yeah, thanks, Michael. Yeah, the next one. This is probably going to be one of the most contentious. I think that's the right word. Anyway, part to doing your installation, the site information drawing. It's a new requirement, and yeah, I'm sure everyone's going to love this part. So recording of that information, the solar system layout plan shall be placed at the main switchboard and or meter box fire panel. The label shall be, that map shall be laminated or protected by a solid clear sheet such as Perspex. Be fixed permanently and in English. Be labeled PV solar site information in white letters with red background. Show the location address as recorded for the installation. Contain a plain view of the building showing location of PCEs, the PV arrays. Contain a legend for the map or clearly label to identify key components and building reference points. Identify on the site plan with the words "you are here." Be as accurate as practicable, and an installation date. I put the words "wow." I thought, yeah, but there's more. Additional information for PV DC systems, clause 5.6.1.1. You also got to put on the map the path of the DC cabling, the location of DC disconnection points indicated by DP, the location of additional load break disconnectors, PV array size, DC voltage, and contain a warning where DC disconnected types can only be operated by suitable qualified personnel. There is an exception. These additional requirements are not required for systems with a calculated PV DC circuit maximum voltage is less than 120 volts DC, and when the inverter is located within 1.5 meters of the PV module, typically when connected to microinverters. but you still need to have a map. It's just these additional requirements. Other labels are required as per section 5. Documentation. At the completion of any installation of the PV system, documentation shall be provided in accordance with the requirements of this section. This documentation should ensure key system information is readily available to customers, inspectors, and I'll probably highlight that, maintenance service providers, emergency services personnel. We want to see installations having this available to the inspectors to be able to see circuit arrangement, all the bits and pieces that you're putting in, all the data, so the inspection can be carried out properly. Commissioning requirements. Clause 6.3.2. It's not too many changes from previous version, but I do have a special note. Part C. Check and record the continuity of all earth connections, including PV module frame earth connections. It's always been there. You must check and record the continuity of all earth connections. What's been added is to check that radio and TV reception of key broadcast stations, essential services, are not degraded when the installation is fully operational. Over to you, Paul.
Thanks, Lewis. And I'd like to thank all of our presenters for presenting on what is a tough topic to talk to, particularly over a webinar like this with over 100 attendees. Just a quick final note that we actually haven't received too many questions or any questions thus far. So if you want to quickly type in your question in the Q&A down the bottom, then we can get back to you after the webinar is finished and collate those answers and put them up on our TKB for you. Again, a thank you to everyone that's attended. That is the end of our webinar, obviously. A big thanks to everyone across Australia who has attended this. It's been such a well-received webinar, and I do appreciate those that have turned up. I also want to thank again the presenters, Lewis, Grant, Michael, and Malcolm for presenting, and the other members of the technical team across Australia from NECA. Other than that, we'll sign off from here. I wish you all a happy afternoon and evening across the country, and we will talk to you through our member services sometime soon. Appreciate it. Thank you.